Yeah, no.
Let you know, 10, 5, and 2.
Sure. Okay, thank you. Okay. Good morning, everyone. Today I'm going to talk about geotechnical design challenges for temporary excavation support at the Arbutus Station and double crossover for the Broadway Subway Project. First of all, I want to thank my company Horizon and my principal Kareem to give me such an opportunity to get involved into this project. And also my senior engineers, Hero and Robert, helped me throughout this project. And as you may know, this project is ongoing, so the information I'm going to share with you today is limited to the published paper, and which has been reviewed by our owner, province of BC, and our client, Broadway Subway Contractor General Partnership, BSGGB. So now what is Broadway Subway Project? It is a 5.7 kilometers extension of the Millennium Line, starting from Clark Station through Broadway and to our Arbutus Station, terminus station. The first 700 meters will be elevated. It is extending from the Clark Station all the way to Great Northern Way, and the rest 5 kilometers will be tunneled under Broadway and to our terminus station at Arbutus. In total, there are 6 underground stations, and at our terminus station, we have the B-line service connecting to UBC. I believe this station is the longest of all. It is about 330 meters long, spanning across 2 city blocks from Arbutus Street to Cypress Street. It has 3 major components: the head house, which is for the passenger to go inside and go down to the platform, which we call the station box, and we have the double crossover for the train to switch their tracks. And you can see this illustration. This is the future Arbutus Station is going to look like. All these pictures I'm going to show, it is downloaded from the Administration of Transportation and Infrastructure website, which is widely available to everyone. Let me show my pointer. So now we talk about our excavation requirements. Overall, the depth of excavation is about 18 meters, and at some areas it's as deep as 20 meters deep. It is a vertical shoring design to support adjacent buildings, both at grade and multi-level underground parking. It also needs to support the traffic deck and underground infrastructure. We have a lot of infrastructure such as storm and sanitary lines, telecommunications, gas, and a BC Hydro concrete duct, and most importantly, the Metro Vancouver Capilano 4 and Capilano 5 water main, which I'm going to call them Cap 4 and Cap 5. Our excavation also includes encroachment and non-encroachment sections. And for all other projects, we will have to do site investigation first. Subsurface investigation was carried out by Golder Associates and EXP in 2019 and 2021. And they conclude that there's a field and superficial silt layer up to 4.5 meters deep over a stiff to very stiff silt spectrum up to 12 meters deep, followed by glacier drift and glacier tail up to 20 meters deep. And we expect the bottom of our excavation will encounter bedrock, which is extremely weak to weak sandstone over mudstone. Groundwater table from the west at Arbutus Street is about 3.5 meters. down to 9 meters at Maple, and go back up to about 4 meters at Cypress Beach, which there is a Berry Creek running along Cypress. And now we talk about our shoring design challenges. We divide this into 6 specific zones. Each zone we have optimized our shoring system for constructions and provide a cost-effective solution. Our shoring system also needs to manage ground deformations with tolerant limits as set by structural assessment for the adjacent buildings and all the underground infrastructure. We also have soldier piles installed in pairs along north and south of Broadway and act as a temporary bridge for the traffic to go over during our constructions. Most of the shoring elements, such as soldier piles, concrete walls, and anchors, will remain in the ground 1.5 meters below to satisfy the City of Vancouver's requirement. Our design solution also needs to be flexible, adapt to changes, and in consideration of construction sequencing, surcharge loading, available materials, and different geometries. In general, there is 4 types of shoring system. The typical tie bed anchors with reinforced shotcrete, pipe piles with tie bed and shotcrete, and in the non-encroachment area, we will have soldier piles with splice and shotcrete panels, and secant piles with reinforced shotcrete and steel waiters tensioned with tie bed anchors. Now we talk about challenges for each zone. The first zone is to the left here is along Arbutus Street, which we need to design to support the CAT4 and the concrete BC hydro duct. Also, we need to design to support the mine tunnel, which is going to be opened in the later stage. Tie bed anchors are allowed in this area, but we have to provide the offset from CAT4. CAT4 is a 1.2 meters diameter water main. It's pressurized, and it's about 2 to 5.5 meters below grade. The north section of CAT4 will stay at this, but the south side of CAT4 is going to be relocated. And the BC hydro duct, unfortunately, we cannot relocate it, so we have to design to be suspended across this excavation. Our solution for the north side for the CAT4 will be installing pipe piles, 6-inch Schedule 80, up to 9 meters long, and with 3 bolts anchor to secure the pipe pile. This pipe pile system acts as a cantilever retaining wall and to provide lateral pressure to support the lateral pressure and the utilities behind it. And to the south side of CAT4, first we need to install tie bed anchors to create a bench for the new CAT4s to be relocated. Then we install pipe piles up to 5.5 meters, and we have 2 ropes anchor to secure the pipe pile system. The overhanging BC hydro ducts will have extra pipe piles on both sides, and with steel structures supporting over the pipe piles designed by others. And for tunnel openings, because we cannot have steel elements, we have to use fiberglass rebar mat and fiberglass anchor. However, because this is a mine tunnel, we can use 35 MPa shotcrete. So this is a picture of what it looked like at the head house area. It is about halfway below the surface. You can see this is the cantilever portion. It's about 4 meters, and below And behind it, this is the BC hydro duct. It's not very clear, but you can see it's overhanging across our excavation. And you can see the orange Thales optical lines and storm and sanitary running across, which is going to be in our Zone 2 challenges. So this Zone 2 is about the north and the east house and part of the north and south excavation of the station box. We need to design to support adjacent buildings, which is they are only at grade structures, plus the utilities that you've just saw. And we have to include construction load and construction traffic over this north portion. Tieback anchors are permitted, and because of this, we have a very typical tieback anchor systems, which have 9 rows of anchors. It's up to 30 meters long, and you can easily include traffic load. And for Zone 3, which is this little yellow area here, we call this the emergency exit stairs. It is not as deep as the main excavation. It's only about 10 meters deep, but we have a very tight space. The exit stairs itself is only 6 meters by 9 meters wide, and the corridor connecting between the stairs and the excavation, the main excavation, is only about 4 by 5 meters wide. If this tight spacing, tieback anchors is not desirable to be installed because of the tight spacing. So therefore, we come to have a creative solution with pipe piles and steel waiters and struts. This will create a box frame structures to secure all the walls. First, we install the pipe piles, and then when we excavate the panels in between, we connect them with horizontal rebars. When we get down, we install steel waiters and struts, weld them together, and make a box frame structure. This top-down solution addresses the space constraint restrictions. And now we get to Zone 4. It is the rest of the north and south excavation up to Maple Street. We have to support multiple levels underground parking on both sides. The excavation getting closer to the adjacent building because there's a fence shaft on both sides. We also, on Maple, we have to support the 1.8 meters diameter Cap 5, which is going across, and it cannot be relocated. This Cap 5 is also pressurized, and it is suspended structurally using cradles and transfer all the loads to the traffic piles by others. However, we have to design the 2 faces, the north and south face, to support the abutment. So our solution outside Cap 5 is the pipe piles with tieback anchors. The pipe piles up to 11 meters long, 10-inch Schedule 80. The first few rows are very steep angles, up to 45 degrees. In this system, you can see we can manage the deformation and to support the load from the soil. This is a picture of this area. The pipe house is up to 5 meters cantilever. And for the solutions for Cap 5, we have to make a bench 5 meters deep for them to install the saddles to support the Cap 5. So we installed pipe piles with tiebacks and additional horizontal rebars to support the wall. The back wall also needs the top of the back wall also need to install the concrete and steel waiters for supporting the top portion of the Cat 5. This is a picture of the Cat 5 spanning across. We have small saddles with steel frame structure, and all the load transferred to the traffic piles. And now we get into the non-encroachment area. It is between Maple and Cypress. We have to design to support adjacent buildings with multiple levels of basement, and of course, utilities. And also we have to design for 2 big openings. One in Maple is about 11 by 19 meters wide. And at Cypress, the even bigger one, 40 meters by 21 meters wide. That is for the TBM removal at a later phase. Our solution outside Cypress will be a braced soldier piles, 3 meters spacing, and we have to install reinforced rebar horizontally between the piles to provide support for the soil. And then we install waders and struts to brace the both sides of excavation together. In addition, for that extra load at Maple opening, we have to have more waders and struts. And at the Cypress opening, we have 2 levels of struts, and we have added a double wader system, which is 2 H-beam stitched together. And then we have 2 double waders, and we have struts to brace across them. This is a picture from another station, but the shoring, the brace and struts are similar. And now we get to the last zone, which is zone 6, which is the east head wall at the TBM breakout. We have to design for traffic load on Cypress, the breakout force for the TBM when it goes through the shoring wall, and we have to design for the outrigger pads when the mobile crane came here and removed the TBM. And of course, at the tunnel openings, we cannot use steel elements for shoring. And thus, our solution will be a secant power wall, 900 meters diameters, with 10 MPa concrete. We have secondary piles with reinforced cage up to the top of the openings. And beside the openings, we have full-length H piles. We also have shotcrete and steel waders with tiebacks to secure this secant power wall. Within the tunnel areas, we'll have fiberglass reinforced mats with fiberglass anchors. As I said, for the TBM removal, we have to predefine a mobile crane before, and to predefine the location and the load that will be applied to this wall and considered and add into our design. Instrumentation and monitoring, we have nano sensors and wall targets installed on every building along Broadway. And on Cat 4 and Cat 5, we have sediment gauges, we have inclinometers, wall targets, and on Cat 5, on the steel structures, we have nano sensors and strain gauges. On our shoring excavation phases, we have wall targets, inclinometers, we have strain gauges on our struts, we have nano sensors on some of the wall, and we have INSAR surveyed for final configuration. We collect all these data and compare them frequently with the predefined thresholds to prevent unacceptable risks, make sure the excavation is safe, and the surrounding buildings and infrastructure is stable. In conclusions, our design challenges require iterative effort to develop a practicable solution. We need to collaborate and communicate with different design teams to avoid conflicts and provide a solution that works for everyone. We have a lot of design constraints, which end up with a more complicated design, including the changes in soil condition, underground utilities, and building basements. However, we accurately gather all these constraints information and came up with an optimum design to provide a better risk management. That's all for my slide. I'm here to thank our client, BSCGP, and Province of BC, and other stakeholders to participate in this paper. And I thank my principal, Kareem, and Hiro, and Robert for helping me out for this paper. That's all. Thank you.